Okay, numbers are plateauing off, so we'll make a start. So another exciting evening with Dr. French running through thermodynamics, which is sometimes seen as a tricky topic, but what you've got to do is see the big ideas and not worry about all the fine detail, because that would require, practicing on questions and so on. So do make notes, pick up the details, and see how you could present a difficult topic in a sort of a way with the use of graphs and images to make it clear and to help you understand. Okay, Dr. French.
Okay, good evening, everybody. Welcome again to the BFO Computational Challenge Seminar Series. And tonight, we're going to have a heated discussion of thermodynamics, which are, don't listen to Professor Hughes. This is a lovely topic, not too hard. But I think probably alongside optics, I think it's fair to say that this might be one which is a bit neglected compared to special relativity or quantum mechanics or sort of mechanics and electrical things. So I think this is my chance to sort of hopefully sell you that this is a really good thing to do. I guess probably was extremely popular a few hundred years ago at the start of the Industrial Revolution. But obviously, in terms of finding energy to make the world work is still an ongoing challenge. And so therefore, thermodynamics is going to be at the heart of that. Here are, first, before I start, here's a plug to some wonderful books, which I highly recommend you should put on your coffee tables. Not written by me. This is written by a guy called Theodore Gray, who I think was Stephen Wolfram's partner for the Mathematica software, if you might have used that before. And it's a tremendous series of books, beautifully illustrated with all sorts of quite eccentric and fantastically detailed photographs. So this is the engines book, which kind of relates to what we're talking about today. But there are also things on chemistry, the chemical elements, reactions, all sorts of stuff. And in fact, there's if you have younger siblings or maybe young children one day, there is the ABC of the elements, which is really rather lovely. So there we go. I got my my sort of 3-year-old nephew to have U is for universe or U is for uranium. That was quite good. So there we go. Right, so we're going to start off. There we go. Throw yourself in. So what is thermodynamics about? Well, thermodynamics is really about energy and about the end. And energy, of course, is the universe's accounting system. So we're going to have a little look at a very almost abstract problem, but actually reveals something if you apply, logical maths to it about our world. And this is about heat engines. So an engine, like the sort of thing that's on the previous slide, so something like this, we've got some engines in a motorbike, we've got a sort of a petrol or a diesel engine, a steam engine. I think there might be an electric motor. I think that looks like an electric motor at the top. So regardless of the details, I mean, these things are fantastically detailed, right? So in physics, we're trying to sort of focus on what are the key essential features of how we can model these things. And if you really strip things back, it's all about energy and also entropy, which might be a new concept for some of you, for the younger ones on this course. So I'll introduce that too. So the things in the red box will start in the sort of top left-hand corner. And we've got the statement of the first law of thermodynamics, all right? And that is energy is conserved in a closed system. So what is our system in this case? Well, basically what we've got is a hot reservoir. So this big red box in the top right-hand corner. So you can imagine a reservoir is something, well, like a water reservoir is something that if we extract something from it, like a glass of water from an enormous lake, the lake isn't going to change appreciably, all right? Obviously, if we drink, millions and millions of litres from the lake, it will go down. But if we just take one glass of water, nothing much is going to change. So a hot reservoir has temperature TH, T hot. And the idea, if we extract some heat from energy from it, we're not going to change its temperature. It's important to note, although we're not going to overtly look at that straight away, that temperature, certainly in Kelvin, is proportional to the mean kinetic energy of molecules, which, if we can ignore any kind of intermolecular forces, is basically the internal energy of some object, some system. All right. So essentially, the temperature is proportional to the total energy. It's a measure of the total energy if we're talking averages here. All right. We'll talk about the kind of the usual flow of thermodynamics is we start off with a sort of fluid-like modeling system Whereas actually what we're doing is we're talking about molecules in, trillions and trillions of molecules in random motion. So it's a statistical theory. And that's what we'll start to look at towards the end of this, this seminar, all right, and how we might model this with computers. So we'll start off with this hot reservoir, and we're going to extract heat Q in. So that's a number of joules of heat which we can use to do something with. So a heat engine takes this energy, which it's liberated from my hot reservoir. That could be some sort of chemical reaction. It could just be you're connected to something hotter than you are, like a hot cup of tea. You stick a plate on it, you extract some of the energy to do some work. There's a device called a Stirling engine, which does just that. And so work is the useful mechanical energy. It's something we're used to, move a stone, pump water out of a mine, drive a car, fly a plane, move the human body, whatever. We've got it. So we are heat engines. Right now, this is what's happening. But we also have an outlet. So we're dumping some heat to a cold reservoir. All right. And it's the flow of heat from the hot to the cold, which in essence drives all the heat engines. If we didn't have a cold reservoir, well, how would that movement of thermal energy, how would it work? And it's interesting that we can't actually set Q out to 0, right? So by conservation of energy, you might think, well, that's possible. Just Q in equals W. So Q out could be 0. Fantastic. That's not broken any laws of physics. Well, unfortunately, it does. It breaks the second law of thermodynamics. And so that rule is that entropy of a system must either stay the same or increase. So what is this entropy? Well, in the classical world, thanks to Rudolf Clausius, it's defined by the heat change divided by the absolute temperature in Kelvin, not degrees Celsius or Fahrenheit or any other exotic measure of temperature. So T is the proportion, it's directly proportional to the mean kinetic energy of molecules. And that's what Kelvin is. So that's what, in classical terms, entropy is defined. Of course, we have, if you've been studying chemistry and a statistical measure of the world, we can have a better definition of entropy, which we'll refer to a bit later. Can anyone put in the chat if you know what that is? So what actually is entropy? So Mustafa says it's random. It's related to that, actually. If anyone's studied this in chemistry yet? Whoa. Things become less optimized. Disorder of particles. Oh, very good. Anango, that's excellent. K log W. Brilliant. Like chaos. This is all the right sort of stuff. So it's actually a measure of the number of ways of arranging energy quanta in a system, which may seem like a really difficult thing to work out if you've got a kind of, Avogadro's number of molecules in a gas. But like a sort of smaller system, you can think of, like a chessboard and how many ways I can arrange, maybe a Go board, actually, that might be better. How many 20 black pieces amongst all the others. Actually, the K log W bit that Ananga's put in the chat, it's easy to think of this as a logarithm. If you're interested in that kind of subtlety, I've got lots of notes. And indeed, that will be in Science by Sim 2, which will be hopefully published within the next few months. I know some of you are asking, is there a book for this course? Yes, I think it's been put in the chat. If not, if my fantastic volunteers could do so, Science by Sim 1 has all that kind of stuff, but Science by Sim 2 will have pretty much everything that's here. Of course, you can download this presentation from the BFO website, which the link is in the chat. So, but going back to classical stuff, the energy change, the heat, divided by the temperature in Kelvin is the entropy change. So let's have a look at this system. Remember, we're not seeing any details of what's happening in the heat engine at this point. It's just it transforms Q in of heat to work and Q out. All right, so Q in's got to be bigger than Q out or W because of that sum. So what we can do is we can look at the total entropy change, delta S hot and delta S cold. So what have we done? Well, we've extracted some heat from our hot reservoir. So we've actually got its entropy to be lost. We've removed some heat from it. That's okay, because the second law of thermodynamics says that the total entropy change of the universe, the entire system, has got to be the same or bigger than 0. It drives time, in fact. So there we go. So if you have a really untidy bedroom, okay, if you tidy it, that's reducing its entropy. You may say, well, this is against the laws of physics. Well, not really, because you've had to put lots of work in to do that. You've expended some heat to manipulate all the things in your bedroom. So overall, the entropy change of the universe is probably increased. So if we combine those two things together, we've got minus Q in over TH plus Q out over TC. And by the second law, that has got to be bigger than 0. Right. So what we're interested in here is the efficiency of a heat engine. All right. And we're going to do some examples of heat engines shortly. But so what is this efficiency? Well, if you look at the bottom of the page, it's the work done divided by the heat input. So if I've got 100 joules of heat to use and I do 50 joules of work, then obviously my efficiency is going to be 50% or a half. So I'm going to call that symbol eta, and I want to find that ratio. So what I want to do is get rid of Q out in this expression algebraically. So Q out is Q in minus W from the first law, and I'm combining that with a second law. So now all the rules are put together. I've got all the ingredients in my recipe. Now I'm just going to manipulate that and see what kind of cake comes out. So this is the expression that sort of I'm circling at the moment. I hope that's nice and clear. So what we do, we want to get W over Q in. So I'm going to divide everything by Q in. And given that's not 0, I can divide 0 by that. That's fine. And so I've got 1 over TH plus 1 minus my efficiency over T cold. What else can I do? Well, if I multiply both sides by T cold, I've got this bit here. And I then got a sort of 1 minus this lot. And finally, if I move W over Q into the other side of the inequality, I've got this sort of situation. So 1 minus eta minus TC over T hot is bigger than 0, or eta is less than or equal to 1 minus the ratio of the temperatures. Wow. So from literally knowing nothing about the heat engine, all right, this could be anything we like. It could be as technical or as simple as possible. But all we know is we've got some flow of energy from a hot to a cold reservoir. And we're obeying the first and second law of thermodynamics. And that tells us that there is a maximum efficiency that is allowed, regardless of the details of the engine. And that's 1 minus the ratio of the temperatures. Okay, so T hot is bigger than T cold, and these must be in Kelvin. Cool, eh? So there we go. That sets a limit on how efficient engines can be. So we're going to now look at some engines, but are there any questions which have arisen from this a rather busy but I think helpful and useful page? Nope, nothing in the chat. Great. Okay, great. Yeah, there's some Q&A, and I think what is entropy again? Yeah, so okay, so entropy, as we're going to define it two ways. So the way that thermodynamics is taught is you look at the sort of classical world where heat was thought to be a kind of fluid-like quantity, all right, like sort of like fluid dynamics, like water, hydrodynamics, you know. Of course, nowadays we have a molecular theory, so we talk about it as a statistical average of molecular motion. But you know, when it was developed, molecules are so small that you can kind of regard this as a continuum. In fact, the borderline between those theories we'll address with something called a Knudson's number a bit later. All right, so entropy at the moment is the heat change divided by the temperature. Okay, and I think these are your resources for the moment. So, I hope that is what you should need. There's plenty on the Eclecticon though as well, and of course in many, many, many textbooks. Right. Okay. Here's a few things. So we're going to refer to. I'm going to gloss over some of the quite a lot of the mathematical details. It's more for inspiration today, but there's a couple of things I think you should know. So if we have a piston, so a lot of what we're going to talk about in engines is actually about using gases. So if you think how a car engine works or a diesel engine, what we're doing is we're getting some fuel vapors and we're combusting it, or we're igniting the gas or squishing it until it self-ignites. And then we're going to be pushing against a piston to do some work. So we kind of want to relate gas pressure. So we're looking at ideal gases. PV equals nRT, pressure times volume is number of moles times the molar gas ratio times the absolute temperature. So we don't really want things like forces and that kind of stuff. We want pressures. So force over area is pressure. And if we sort of squish a cylinder like this, you think about the work that's done on the gas. It's the pressure times the area times the distance it moves, all right? And the distance, if you look at my little thing I'm highlighting, is going to be the volume divided by the area. So I'm assuming my piston has a constant cross section. So we have a nice expression, which is the work done on the gas is minus the pressure times the volume change. Now, I've used calculus notation here. These changes are going to be small because you might find that things like pressure and indeed volume change a little bit as it's squishing. All right, so we have to add up these little changes. That process is called integration. So we can also look in terms of very small changes, what's happening to the internal energy. So if you think about what we did before, our first law, so our internal energy is the heat that we add and the work done on upon it. Now, remember, there's a minus sign there because if the volume change is negative, then we've done work on a system. So we need to cancel that negative delta V by a minus sign there. So a positive amount of work is done on my gas. So if I add some heat to a gas, I ignite it, for example, a chemical reaction, explode something, and I compress it, those two parts is how I can increase its energy by work and heat. Okay, so I'm going to quote this for now. So, and there's some nice subtle arguments of where the half comes from, but the internal energy of a gas is actually directly proportional to its temperature in Kelvin. All right, and if we're talking moles of gas, so human-sized units, the molar gas constant, 8.314 joules per mole per Kelvin, times the temperature, times the number of moles, multiplied by half and the number of degrees of freedom. So if you've got a molecule which can move in 3 dimensions, alpha's 3, it might stretch a bit, so you can add to alpha. It might rotate, so you can add to alpha even more. All right, and this is all related to something called the heat capacity. How the sort of internal energy varies as you sort of vary temperature, or perhaps pressure, or perhaps volume. And so the greater the number of degrees of freedom, you've got more ways of storing energy, so your heat capacity increases. But really, those things only happen at really high temperatures. So alpha is often 3. So if you look at an A-level textbook, this will be 3/2 nRT is the internal energy. So but exactly where that half comes from, that's quite an interesting story. So there we go. Let's just give you some ideas of how temperature relates to internal energy and how heat and work relate to internal energy. So, oh, Hassan has said 4 dimensions. Wow, gosh. So yes, I don't know if that would. I'm not sure. I mean, we live in a kind of 3-dimensional space, which of course evolves with time. But I don't know if the sort of thermodynamics of general relativity. But I think that's probably a little bit outside the scope of this talk. But a good question. Right. Okay. So these are the details in the boxes are really for reference for later. And if you actually want to do these models yourself, because remember, that's the whole point of this kind of enterprise, is that we give you recipes and you try to put that into code. The purpose of these talks is to give you inspiration, really. This is how we might sort of put together what we call a gas cycle. So a heat engine, how might that work? And basically what we're doing is we're going to track a graph of pressure versus volume. Because these are the things which, so pressure, volume, temperature are the only parameters in our gas, as long as there are no leaks. So this is our ideal gas equation. And so, I think combustible fuels, etc., in gaseous form, we're going to assume that this is true. So there are sort of 4 processes that can happen. We can have a constant temperature process called isothermal. And that is when PV is constant. Whose law is that? Can you put that in the chat? Yes, good. That is Boyle's law. Fantastic. So rather than having to learn lots of different laws, all we need to know is the ideal gas equation. And that's even better because we can say, look, when the number of moles of gas or the temperatures are constant, then PV is a constant, right? That's Boyle's law. Okay, so Boyle's law, you've probably done this at school. You have a kind of cylinder a bit like this, but with a little sort of a screw on the end, and you screw that very, very slowly, and it slowly compresses the gas. And so you're doing some work, but the idea that the temperature remains the same. So the work you do is balanced by the heat that it sort of transfers to the environment. So the temperature remains the same. So there we go. If you actually do the math, so if you actually sort of work out this expression and integrate it, nice little exercise, what you'll find is because V is proportional to 1 over pressure, or sorry, rather pressure is proportional to 1 over volume, you'll find you get a logarithmic variation of volume with the heat or indeed work that you put into it. Remember, the heat input is the work done by the gas, not on the gas, because the total internal energy must be constant. Why? Because the temperature is constant. And we said that total internal energy is proportional to temperature. So that's one of the processes. This is a slightly more sophisticated one, I think, which has got a constant entropy process. So this is when no heat is exchanged. How do we know that is? Because that's the definition of entropy by Rudolf Clausius, with a fantastic beard there. Look at that. And if you do some calculus, again, you can work out the expressions for the work done versus the volume. And it has this sort of power law involving this ratio of specific heats. So this is where you're transferring energy to a system. How much does it go up with temperature? With constant pressure or constant volume. And it turns out that that's actually related to the number of degrees of freedom of your gas. So 1 plus 2/3 or 5/3 is what it is for just an XYZ moving gas. All right, but obviously it's a bit different when alpha is larger, when things are hotter. So what we can do is something called a Carnot engine. So this is it's very. I don't think you can really make one of these, but it's an example of a heat cycle. So let me just explain. There's a few bits of this graph. We'll sort of take our time looking at this. So what I've got actually is not pressure and volume, but temperature and entropy. Why on earth have I done that? Well, hopefully you can see that I've got a rectangle. So the most sort of efficient engine ever, okay, is going to be represented by a cycle in either temperature, entropy, or pressure and volume. Okay, and just before we do that, I think there's a question about what's gas degrees of freedom, this alpha parameter. We'll only use it once, which is this one, but it's the number of movements. So for example, alpha is 3, means I can move a molecule in X, Y, or Z. All right, okay, and yes, efficiency is the goal of what we're trying to figure out. So we've got an engine which goes from these 4 parts. So a Carnot engine basically works in this way. So what we do is we expand a gas at constant temperature. That's from 1 to 2. And so if it's isothermal, that means the temperature is a constant. So my gas, I'm starting at 90 degrees. So let's just say we've got a process that my hot reservoir is at 90 degrees. I've got a cold reservoir at 20 degrees. And by some means cunning, I can expand a gas with some pistons, and not far off. If you put a Stirling engine, it's like a sort of little sort of cell, which there's something which you can move, a little piston on top of a big cup of tea, and that can actually drive a piston. If you've not seen that in school, you can have a good look on the YouTube videos. I think I've got one on my website. What then happens? You've expanded your gas. Well, you've you've expanded your gas, and then what we're going to do is we are going to expand it a bit more at constant entropy. All right, so we're going to go from 2 to 3. Now, at constant entropy, that means we're on, we haven't changed our entropy. And then what we're going to do is we're going to compress it at constant temperature. All right, and then we are going to compress it a little bit more to get back to where we were at the start. And that is a gas cycle. It may seem rather abstract at the moment. Why have I done it this way? Well, because the area under that is very easy to work out because it's a rectangle. So what has this area got to do with efficiency and work and all that kind of stuff? Well, let's look at the first law of thermodynamics. Okay, so if you see, so our first law, this is the total, this is a small change in the internal energy of a system. This is the heat added to it, and minus PdV is the work done on a system. Why is it minus? Because dV is negative if we're squishing something. Now, here's a tedious thing to talk about. Ha ha ha. Collective groan. So delta Q over T is the entropy change. That's the definition of entropy. So we can swap our heat added to TdS. All right. So my first law of thermodynamics, I can write like this. Now, if I go around a whole cycle, so I'm squishing a piston coming back, I'm going from one side to the other. So if you're like in a petrol engine, for example, you do swap the gases at the end. But essentially, you start off, where you end up where you began. Otherwise, it's not a cycle. So in terms of the total energy change around my cycle, that's going to be 0. All right, because we started where we finished. So if you add up all these little changes, and that's what little circle means. It means we're adding up all the little DQs and work done around this path. Then that bit is going to equal that bit. All right. So in other words, P dV is equal to the integral of T ds. Now, what does that actually look like? Well, think about it. It's a temperature times a small bit of energy. That's what that is. That's like a rectangle. And we're summing those all over the whole path. Now, if you think about it, what that means is that literally I want the area under that graph, right? So the rectangle. So the work done by a heat engine is the area enclosed by the sort of path in the temperature entropy space, or, and we'll look at this in a moment, the pressure volume space. Now, the reason I've done this first for a Carnot engine is because that's a rectangle. So that's dead easy to work out. So we do the temperature change multiplied by my entropy change. Now, turns out, and this is something you'd go back for an isothermal process, is that the heat or the work done goes like nRT log of V. That's because we're using Boyle's law, the temperatures are constant, etc., etc. All right. So when we work out a change of volume, we've got a kind of 1 over V there, right? Because the pressure goes as 1 over volume. So if we divide that by the temperature, we've got this thing I'm circling. So if you put that in, the work done, you can literally just write down in terms of the temperature difference and their volume differences. So that's one of my inputs for this. Think about the computational part of this. So my volume change, V1, I'm going to start off as 0.1 meters. And I realize I've not got it written here, but we need a sort of what a V2 is as well. So if we sort of like work out what the efficiency is, the work done divided by the heat input, we basically can put this expression here and divide it by the heat input, which I've got here, which is the same as this, but of course I'm multiplying it by T hot. And you'll notice that the logarithm bits cancel. And in fact, the molar gas constant cancels and the number of moles cancel. All we're left with is 1 minus the ratio of our temperatures. And if you recall from the beginning, that is the maximum efficiency of any heat engine. So what Carnot, Sadi-Carnot, I don't know if I've got a picture of him, but there we go, Nicolas Leonard Sadi-Carnot, 1796 to 1832. So he's credited with inventing this, which I don't think can actually be realized properly, but it is an example of an engine, a heat engine, which is of maximum efficiency. So what does it look like in pressure volume space? If we've got some sort of piston, imagine this is working, what would it look like? And so what we've got is a piston here. So what are my inputs? Well, let's say we've got some, so in terms of volume V1, it's 0.1 cubic meters. So 1 on this scale. And what we do is we expand it isothermally at constant temperature. And in order to do that, we've got to add some heat. Okay, so we add some heat and that does some work. All right, well, we do some work on it, basically. We expand the gas. So it's there. So there we go. And then what we do is we expand the gas a little bit more. All right. so we're doing work is done by the gas. It's expanding into the atmosphere. And then what we do is we let out some heat. So we go from 3 to 4, and the gas will compress. And we're assuming that's done isothermally. In other words, without any change in internal energy. So the work done sort of on the gas equals the heat that is extracted from it, Q out. And then we have to go back to where we started. And we're going to assume that's done isentropically. So no heat is exchanged. So basically, all the work done goes into the change in internal energy. So there we go. And of course, in this graph, you'll notice there are curves for each one. And so if you want to try and model this, you've got to try and work out how pressure and volume change for each of these. But of course, you know that already because this bit here, the red one and the blue one are using Boyle's law, and the green one and the black one are well, we haven't met this yet, actually, but this is when we have an isentropic system. Actually, we have met it. So for an isentropic process, PV to the gamma is a constant, not PV is a constant. There we are. So there we are. That's just an example of how we can turn a sort of generic process like this into something which we can model. So I'm going to show you sort of how I would go about this. Again, you need to sort of pull up all the formulae, etc., and work out all the bits. But this is a screenshot from Excel. So let's look at the real one. Let's get out this. And I've got some Excel sheets, and you can download this from the Eclecticon. So this is the Carnot cycle. So I'll zoom in as best I can so you can sort of see what's going on. So what we got, these are our input parameters. So when you're building computer models, you need to think really carefully about what the inputs are, what the outputs are, and then the stuff to calculate. So my inputs are going to be things like the hot temperature reservoir. So let's go and make that, let's say that's 80 degrees, all right? Let's make the cold reservoir a bit colder. Let's go for 5 degrees, something like that. And let's say I've got 1,000 kilograms of gas. That's all right. And then I work out the, there's two volumes I need to add here. So there's the volume of the gas at the lowest volume and the highest pressure, so this bit here, and the volume of gas after the isothermal stage, so this bit here, so 0.3. So they're kind of the volumes at the red part of the curve are my inputs. Then I've got the number of degrees of freedom of the gas. So I don't know, let's make that a bit more than 3. Maybe it can stretch and rotate a bit, so make that 5. Hasn't really made much of a difference in terms of my graph. And I've got the molar mass of gas, so that's roughly air in grams per cubic, grams per mole. And so what I can then work out are the heat inputs during the isothermal stage in kilojoules, the heat output, etc. And so this is 21.2%, which should be the exactly equal to the theoretical efficiency. I don't know if you can see the formula I've got at the top there. That's 1 minus the cold temperature in Kelvin divided by the hot temperature in Kelvin, which I should have here somewhere. Yeah, so C 41. There you go. So these are my reservoir temperatures in Kelvin. So what you don't want to be doing is using Celsius temperatures here. So there we go. And so let that refresh a bit. And so you can get this whole thing to move. So we can make, say, the hot temperature, I don't know, let's change the gas volumes a bit. Let's say make that 0.05. Okay, we can sort of vary our graph. And has that actually updated? I think it has. There we go. So that's now updated my graph there. If I make that a bit bigger, let's go for 0.2. There we go. My graph has now changed. So everything about this it varies depending on what these input parameters are. How have I done this? Well, each of those curves are plotted by this sort of a grid here. So I've got the 4 stages, and I've got pressure and volume. And what I've got is I've got a volume fraction from 0 to 1. And I work out the kind of maximum, the coordinates of each of these points, which is given in this little bit here. So pressure 1, volume 1, pressure 2, volume 2, etc. And so my volume fraction is a sort of, I divide that up into 100 bits. And so that's how I get nice smooth curves. So you could easily, well, not easily, but you could, well, probably you could code that up in Python or something like this. There we go. So that's an example of how we could do a practical gas cycle. Well, not really practical because it's a Carnot engine, but something that you could use for a real engine. So I think some of you might be interested in Formula One or transport or something like this. I'm not going to say that. Let's look at maybe a more practical engine. So if I just go on to how we do time, yeah, all good, I think. Yeah. So this is for a diesel or a Otto cycle. So these are basically combustion engines. Now, hopefully, we will get away from these to electric cars or hydrogen cell things. But at the moment, diesel and petrol are still quite important in the world. And basically what happens is that we sort of open a valve. And we've got this sort of thing which rotates at the bottom. And this is a piston. And so we bring in some fuel mixture. All right. It might be compressed. And if it's diesel, for example, it will basically compress and then it combust at a certain pressure. If it's a petrol engine, you'll have to sort of use a spark to cause that explosion. And then you basically get rid of your exhaust and then the whole thing starts again. So that sort of 4-part system basically describes how most of these sort of engines actually work. So what we can do is we can break this down into 4 stages. They're not quite the same as the Carnot cycle. So this is a petrol engine. This is a Ford car at the top. That's a Ford EcoBoost DOHC engine. Looks rather beautiful, actually. It probably doesn't look like that after a few hundred miles. And that was Nicholas Otto, who I guess we credit for inventing this. And so if you just have a look, so never mind some of the maths in the corner, but the graph and the inputs, it's slightly different. So what we do is we have an isentropic or an adiabatic, a constant entropy compression. All right, so basically what we do is we take some air in and we squeeze it. And we squeeze it without any heat change. It's probably not exactly how it works, but that's what our aspiration is. And then what we do is we ignite the fuel vapors. Kaboom! All right. So Q in comes from combusting the gas. All right. So it's actually liberated from the molecules in the fuel mixture. And so the way we model this is that you're going to get a massive jump in pressure, but not much of a change in volume at that point. So this is what we call a constant volume or isochoric stage. And then what we're going to do is we're going to expand the gas. We're going to push the piston. This is the power stroke. And we're assuming we're going to do that without any change in heat. And then we get to this point here, the maximum volume again, and then we're going to let some gas out. And then we'll start again. So based on what we looked at a couple of slides ago, the area under this graph, so the integral of pressure times volume going all the way around the cycle is this area here. That's the work done. And that's what we want to maximize compared to the heat we put into it. And so it turns out you can work through in a very similar way that we did before. Alas, it doesn't look like a rectangle in temperature energy space, entropy space. But you can do it. That's the expression for the work. And you work out that it's 1 minus square root of some ratio of the volumes to the power of this little thing gamma minus 1, which is related to our specific heats or indeed the degrees of freedom. So this is not quite as efficient as a Carnot engine, but it's not bad. But of course, this is a practical thing. We can build cars like this. A diesel engine is very similar. I was going to show you a picture of that. Here's an enormous diesel ship. And if you can see the picture at the bottom, that's one of the engines in this China shipping line, a vast tanker. So the little person is 1.85 meters at the bottom there. Just gives you an idea of the scale of the diesel engines inside the ship. So basically, our whole kind of modern capitalist world is really based on very sort of cheap shipping that is moved around, ISO containers usually. And this really only works because of diesel engines. So if we want to maintain our quality of life, we need to replace these with something which is not based on fossil fuels, but that's going to be quite a challenge. Maybe the answer is using wind, going back to the age of sail, perhaps. The thing on the front, just out of interest, is something which reduces bow waves and reduces the friction of the water as it moves through the ocean. So for a diesel cycle, it's quite similar. But in this case, what we do is we have our isentropic or adiabatic compression all the way to maximize the pressure, and diesel fuel will then combust itself. All right, you don't do that with petrol. It's something called knocking, which you get. So we have to use a spark. But for diesel fuel, it's a bit heavier. Then we can actually do that. It will just self-combust. So what we have is that the heat input then is not at constant pressure rather than at constant volume. It's called an isobaric. Think like barometer pressure, right? So it's a slightly different cycle, but it's very similar. We have to work out the air under this. This is a bit more complicated, but you get something which has a similar form to the efficiency. So that's a nice little exercise you'll do. Probably, I think Katie's on the call, probably your second or first year at university is actually working through all of that. Anyway, so again, you can sort of make it into Excel sheet or indeed a computer program. So I think what we'll do is we'll move on a little bit. How are we doing for time? I'd like to, I think I might sort of leave Newton's law of cooling for another day. And I'd like to talk a little bit about this, which is a random walk. So I'm going to just sort of go to this slide, I think, here. Yeah, here we go. So you've probably seen this little simulation by PHET. I think I'm going to move this onto the page. It's brilliant, actually. And you click on the states of matter, and you sort of see, what a solid is. This is neon, and you kind of like say, well, what's the liquid state? And what you see is that rather than a solid state, everything's vibrating about fixed positions. In the liquid state, it kind of flows everywhere. But you still have lots of intermolecular forces holding the structure together. And then in the gaseous state, so if we kind of heat this up, we give it some more kinetic energy, and eventually, they're all bouncing around elastically, hitting the sides of the walls of the container. And that's what we think of as an ideal gas. This is exchange of momentum as it's bouncing, around the place. And you've got some fun things like if you use water, for example. So this is water vapor, but the water molecule has this sort of bent structure to it with the hydrogens and the oxygens. You can see this has got more degrees of freedom if they're rotating and spinning around as well as just translating. So alpha will be bigger than 3. And then if we turn it into its, if we cool it down, we get to the liquid water eventually. Let's get for liquid water, let's short circuit a bit. But then if we cool it even more, something fascinating happens. It expands, all right, which is odd because the water has this bent structure. The hydrogen bonds mean they're kind of holes in the structure. So solid water is less dense than liquid water. But the whole simulation is based on, in this case, several hundred, but in reality, trillions and trillions of molecules moving in random motion. So how do molecules move? And in fact, when we come up, this is all to do with Robert Brown, Brownian motion. So we're going to have a little look at how random motion might work. And I think so. We always try to do a little bit of coding live in these seminars. So we're going to have a look at some kind of random walk. So I'm going to do a very simple one for you live, then I'll show you a slightly more sophisticated one. So I'm just going to go and quit that for the moment. This is MATLAB, and I'm going to make a page, and I'm going to have a particle which basically is going to move in 2 dimensions in a very random sense. So what we're going to do, we're going to have a step size of 1. So L is going to be my step size. And what I'm going to do is I'm going to start my X and Y coordinates at 0. And what I'm going to do is I'm going to say, well, let's say I'm a molecule, I'm a gas molecule, and I'm going to move in time delta t. I'm going to move L equals 1 unit, but I'm going to move in a completely random fashion. So although my step size is constant, the angle that I move between steps is completely random because I'm being bashed into by lots of other things. So what I'm going to do is I'm going to go for a random jump, basically. So we'll go for n equals 1 to, I don't know, let's go for, let's just define a big number, shall we? So let's go for n equals 100,000, 1e to the 5. And what I'm going to do is I'm going to go around a loop. Let's just save this into this code. Let's call it some random walk demo. So you could do this in Python or any language you like, or even in Excel. And what I'm going to do is I'm going to work out what my next x position is. So x is going to be the previous lot of x's. And what I'm going to do is I'm going to have L times cos of an angle. So what I'm doing here is I'm adding a new position to an array of x, and we'll see how that builds up. And I'm also going to do the same for y. So y L times sine of theta. Why have I done sine and cos? Well, these are going to be the projections of my x or y based on my random angle. So I'm going to choose a random angle, which is going to be 2 pi radians times a random number. So rand, if I execute that, gives me a random number between 0 and 1. So I'm saying, okay, in each of my my iterations, I'm now a little particle. I'm being bombarded by others. So I'm going to move in a completely random angle direction, but I'm going to make a step size of 1 unit. So what's going to happen? Well, let's go and run this loop. Let's just save that. And what I'll do is I'll hover over this bit here and run it. So there we go. So y and x are 0. So if I keep stepping through this, let's just go around this loop a few times. So there we go. So n is now 8. And at my x array, I've got an array of random values of x, which are incrementing. Okay, it doesn't sound so exciting so far. Well, let's go and plot this. So if I then plot x comma y, And let's have X. Well, let's not bother with the X label. Let's just plot it. So if we do this and run it, right, that's gone around 100,000 times. And oh, what we need to do is not have we need a very tiny marker. I think it's rather too many ones I've got here. Oh, I know what I've done. So we need to add to the previous one. That's what we need. So what we need to do is we'll say the next X is the previous one plus this one. Okay, so we've not actually got a walk there. That's just a series of random numbers. Or what I could do is the cumulative sum of those. That might be quite a good idea. Let's go and do that. So let's work out. No, I think it's no. Well, this will be more clear. So my next position is the previous one. So X end is the last element of X, and I'm going to add my step to this. So Y end. There we go. We're good. So there we are. There we go. Get rid of X here. So I've got my last value of X, and I'm going to add my step to it. So hopefully that should work. Let's sort of see. It's done that 100,000 times. There you go. So what we've got is a rather beautiful, sort of fractal path that we've created, which is, so I think it starts at 0, 0 there, and we've ended up somewhere up here. And this could be the path of my molecule as it sort of bounces and bashes into other things. And this could describe, and looking at this under microscopes of pollen grains, this inspired Robert Brown to kind of come up with the idea that maybe there are things we cannot see which are bashing into my pollen grains. Hence the idea of molecules, probably the biggest idea really of physics in the last few hundred years. We can make it a much more efficient version of this program, of course, by vectorizing it and defining lots of things. So this is took a little while to do 100,000 times around that loop. Well, that's quite impressive. So here's one I made earlier, which is basically the same thing, except what I'm doing is I'm doing a loop of P random walks. I'm going to do 100 of them, 100 different ones. I've got 10,000 steps, not 100,000. And this is the function which does it. So what I'm doing is I'm basically have a random angle, but I've also got elevation and azimuth as well. So this is a 3-dimensional random walk, but essentially it's the same thing, a fixed step size. So if I run this, you'll see that this is a lot quicker. There you go. It took almost no time at all. If I basically make this bigger, each of my random walks I've made a different color. And to show you that it's 3D, I can do this. All right, so hopefully that's got to come out. There we go. I don't have a particularly powerful computer. It's relatively modern. It's about 2 years old. But this is something you could do on a laptop quite easily. All right, not bad, isn't it? So there we go. That's a sort of maybe the trajectories of a gas. So there we go. That gives you an idea of sort of molecular motion, and sort of how might we kind of combine that together? Well, there's this sort of idea of a mean free path, which is basically the distance that you move before you hit something. So that was the L that we just used in our simulation. How far does a molecule move before it bashes into something else? And it turns out that you can actually relate that to for an ideal gas, things like pressure, temperature, the molecular dimensions. I've got this sort of derivation in my book. And so if you divide that by the sort of scale of the molecule itself, you get something called the Knudson's number. And so if that number is huge, several hundred, that means that the sizes of the molecules don't really make a huge difference. It's going to travel quite a long way before it hits another molecule. So for an air molecule on Earth, that's about 300 and something. So actually our ideal gas thing where little molecules are bouncing around is quite good. But when we're in a fluid, that's not really good at all, because basically the molecular dimensions are very close to the distance between the molecules. So in that case, the intermolecular forces, things which make it not a gas, so PV equals nRT doesn't work anymore. That's when the Knudson's number is close to 1 or less than 1. So this is really quite useful because we talk about when our models themselves are good ones. So if the Knudson's number is basically bigger than 1, then our statistical kind of idea of jiggling molecules bashing into each other is perfect. But if the Knudsen number is a lot less than 1, we've got something like a fluid where all the molecules are basically in contact. So I think we've got some time for just a couple more bits and bobs. Do we have any more queries? So we get some of the Q&A. Anything that's come out so far? Nope. Okay, right. So what we'll do, here's the example of a random walk. So this is a little bit different. So I did some 2D ones because they look prettier. But in a sense, we could go in one dimension. And basically, we could go forwards or backwards with a random sign of our steps. And if you do that enough times, you can show that the root mean squared displacement goes as the square root of the number of steps you've done. So this case, it's 10,000 steps. And I've plotted this sort of L root n, and you can sort of see as an average of our random walks. So I've got 1,000 random walks here, and I've averaged over those. We get quite close to this. So there are some sort of very nice statistical arguments we can use for how things can move statistically. So just sort of bring this all together. How does this relate to things like temperature and entropy and all that kind of stuff? Just a few random walk pictures here first. There we go. I think we've done this one. Right, so I was going to move across here. So basically, the person really to look at is this guy called Ludwig Boltzmann. And so a little simulation which you can do goes like this. And you say, right, rather than having, we know that atoms exist. All right, we've got this idea from Brownian motion. And we've got this sort of idea of conservation of energy. Well, let's say we've got, say, n atoms or n molecules, and we've got so many quanta of energy. Of course, this links to sort of quantum mechanics as well, that we know that certainly with light, the energy comes in packets, all right, photons. So the idea that we can have a sort of a discrete number of energy bits, if you like, for each of our atoms. And so what you might want to say is, okay, well, let's have a think about having n boxes. In our case, I think I've got 10,000 boxes, and I've got 500 quanta of energy. How many, if I randomly allocate that, all right, and I do that, again and again and again, what's the sort of probability distribution of that allocation? And so what you find is that the highest probable is when you've got, boxes with no quanta of energy, right? Because I've got less quanta of energy than the number of boxes. And you'll find that probability goes down exponentially, all right? And so trying to figure out what that curve is, it turns out, and with a few other arguments too, that you have this thing called a Boltzmann factor. So the probability of having n energy quanta in your box on average is related to an exponential, which in turn is related to temperature. All right, and this law crops up everywhere, from chemistry to quantum mechanics, all over the place. And it also relates to entropy, because entropy is the number of ways of arranging energy quanta. In other words, exactly what we're talking about. All right, so how many ways can we arrange n quanta of energy in big N boxes? All right, so Boltzmann, what he did is he sort of linked this idea of disorder, a number of ways of arranging things, to the sort of stuff that we've been talking about in the classical world of heat and temperature. So that's a slightly longer story for you to look at from notes, etc. But that's the kind of guts of it. It links the statistical world of random movement to the classical world of heat and energy. So I think I'll leave you with this, which is something which all of you will meet available. It's the Maxwell-Boltzmann speed distribution. So this is all about the probability of finding molecules that have speeds within a certain range. And because speed is related to temperature, because the E means the expected value or the average value of your energy is proportional to 3/2 K Boltzmann temperature. So if you go up to moles, that's where we started this whole talk. All right, so the average kinetic energy is proportional to the temperature. And what you find is that you can actually work out what the probability density is, and it has this Boltzmann factor to it. There's a few other bits too, which are all to do with the ways that you can arrange a velocity vector in 3D, but essentially you can derive a curve for what this is going to be. And so what you do is you work out the error between, let's say, 500 and 1,000 meters a second. And the area under that blue curve will give you the probability of finding a molecule with a speed range. It's like the normal distribution, if you've met that in maths yet, or anything like this. And you can work out things like the root mean squared velocity and indeed the average energy as well, which gives you this. So Boltzmann's work is absolutely amazing because it links the statistical world of averages over vast numbers of molecules to our classical world of pressure and volume and temperature and work and entropy and heat engines. So there we go, a very quick tour of an amazing subject, and there is so much here that you can really get your teeth into, but only when I think you've coded up some models. So for my recommendations, what would I do? So for example, the Carnot or the diesel engine, aspire to make one of those heat cycles, figure out what the inputs are, follow my lead, code it up yourself. You'll really understand what all those steps are, isothermal expansions and isentropic parts. If that's kind of been a bit bamboozling in this hour, then you need to kind of do this yourself, and that's a much better way of doing it. And then from the statistical ways, something like plotting this and having a go at this simulation. This is something that's quite simple. Literally n boxes and m quanta, and randomly divvy out, figure out how to do that in code, randomly divvy out the quanta in the boxes, and then work out how many energy quanta are in each box on average, and plot that, and you'll get something that looks a bit like this. So unless there's any questions, thank you very much for your attention. Good luck in picking your models. We're getting quite close to the release of the challenge, which we'll do in a few weeks. So thank you very much indeed. Good night.